Hello, this is Chapter 6 graph. So we are studying how to represent graph. Okay, so here there are several methods of graph representations. Represent means that how we model, how we model graph in data structures. So the first method is adjacency matrix. Adjacency. Okay, so this method uses matrix data structure, and the matrix uh, value means that if value is 1, then there is edges. 0 means that there is no edges. Okay, this value means uh, existence of edge in the graph. That is adjacency matrix. And what is adjacency list? Okay, list, linked list, of course. So this adjacency list express the graph using linked list. So if there is some edge to the other vertex, then this linked list has this node information. Okay, and adjacency multilist, no, we will skip this one, of course. So weighted edge is not graph representation. This is a method how to represent weight in each edges. So there are only two methods we will look at, and also one more additional method is compact representations. Okay, so there are three methods in total in this chapter 6 to represent graph. There are three methods. Okay, let me explain each method one by one. Okay, this is adjacency matrix. Adjacency matrix, what was adjacency? So if we consider two vertex like U and V vertex, and there are one edge between these two vertex, then U is adjacent to V, and V is adjacent to U. Okay, so adjacency means relationship between two vertex, and this edge is incident to U and V. That was an incident terminology, and this adjacency matrix uses adjacent relationship. Okay, so if this graph G has n vertex, then this adjacency matrix becomes two-dimensional array, two-dimensional matrix. The size is n by n. N was the number of vertex n. Okay, this n, this A matrix value is 1, becomes 1 if there is edge between Vi and Vj. Okay, so these are matrix. So there will be 1, vertex vi in the row, and there is vj in the columns. So the value of ij becomes 1 if there is one edge between them. Of course, 0 otherwise. Okay, so that is adjacency matrix. It's a very simple definitions, but this representation is a very, very useful method. Okay, so if we define adjacency matrix like this one, of course, for undirected graph, adjacency matrix becomes symmetric. Okay, and for digraph means that directed graph. For digraph, of course, the adjacency matrix becomes asymmetric. Yes, asymmetric. Asymmetric means that no symmetric. Okay, negative over symmetric. Okay, that is, of course, and trivial result of this adjacency matrix definitions. Okay, let's go on. This is example. Example of undirected graph is here, G1. And G1 can be represented like this one. So 1, 2, 3, 4. So number of vertex is 4. So the adjacency matrix becomes 4 by 4. Okay, so 4 by 4. So each row means that I row, and each column means that J. So this means that VI and VJ has H between them. So VI is 4. No, 3. 0, 1, 2, 3. 3. And this is 1, 0, 1, 2, 2. Yes, this edge, there is this edge in the graph. So the matrix value 3, I. This is a 3, 2. Okay, becomes value 1. Okay, yes, that is adjacency matrix. How about this one? 0. So there is no self-referring edges. Okay, this is not exist here, so this becomes 0. Okay, you can see that this graph G1 is a complete graph. So that means that every edges are connected with direct edges. Okay, so every values are 1 except diagonal element. Diagonal element means that it will loop itself edges. So there is no loop edges, self loop. There is no self loop. Self loop means that this one. This is a self loop edges. So this self loop edge is not allowed in graph. So in diagonal of adjacency matrix, values are every zeros. Okay, and what about G2? G2 in this example is a directed graph. So from 0 to 1, there is one edge here. So from 0 to 1 here. This one, this value 1 means that there is edge from 0 to 1. And what is this one? This one is from 1 to 0. So this edge. Okay. And how about this one? From 1 to 2. So from 1 to 2, this is a 2, index 2. So this value becomes 1. Okay, as you can see that this is a undirected graph. G1 is undirected graph, so this adjacency matrix becomes a symmetric. But G2 is directed graph. This directed graph will create asymmetric uh, matrix. Okay, so we need because this undirected graph is symmetric, so we need only half of the element size is needed. So n square is total number of element in the matrix, but we need only half like this one is needed because the other half is the same. So we need only half of the elements are needed for undirected graph. But for directed graph, we need all element. Okay, so that is n square. And this is another example here, G3. So G3 is not connected. Okay, there is some disconnection between this one. So, but there are 1, 0, 1, 2, 3, 4, 5, 6, 7, yes, 8 number of vertex. So the adjacency matrix becomes 8 by 8 two-dimensional array. And this are disconnected. So we can see that there is some cluster or subgroup to represent the left graph and the right subgraph. Okay, and all of the other elements are 0, means that these two components are not connected. This is a G4, okay, not G3, yes, G4. So G4 is here. Okay, this is an example of adjacency matrix. So this method, adjacency matrix, has many advantages and disadvantages. But this is a merit, means that advantage. Good point. So to determine the connection of a vertex is very easy. So the degree of a vertex is the same meaning. So the degree means that if we sum all of the values in one row, okay, so there are one matrix here. So degree of a vertex I means that every element summation, sum of every element is equals the number of connection. Okay, that means that degree of the vertex. This is a undirected graph. For directed graph, row sum is out degree. Okay, out degree, and the column sum is in degree. So row sum means that if this is adjacency matrix, this is a row sum. And column sum, what is column sum? This is adjacency matrix, then this is a column sum, and this is a row sum. Okay, so row sum means that out degree. Okay, yes, it's the calculation of degree is very easy for adjacency matrix. It is an advantage of this representation method. Okay, second method is adjacency list. This list means that linked list. So we can represent adjacency vertex using linked list. So replace n rows of the adjacency matrix with an n linked list. Okay, this is how to represent link node. So this is a one node. This means the vertex name. And this is a next vertex link field, self-referential link field. Okay, and this is a example of adjacency linked list. Okay, so for every vertex 0, 1, 2, 3, they have linked list to point to the adjacent vertex. So for 0 vertex, there is 3, 1, 2, 3 vertex adjacent. So we have 3 linked node from zeros, 1, 2, 3. Okay, and how about for 2? 2 node, 2 vertex has 3 adjacent vertex. So in linked list, there are 3 nodes which are linked by vertex 2. Okay, in this way, you can represent every graph using linked list, adjacent linked list. Okay, so this is a G3 was a digraph. So for digraph, also we can represent using linked list. For 0 has only one outlink. Okay, and for 1, there are 2 outlink. So 0 and 2 are edges, outgoing edges from this vertex 1. And there is no edges outgoing from vertex 2, so there is null. This means null. Linked list. Okay, in this way, you can represent every graph using linked list. Yes, linked list is a very, very universal, very, very general method to represent a data structure. So every graph can be represented using linked list. Okay, and this is another example, G4. So G4 has disconnected graph, but linked list representation has no difference. It can represent every incident node using linked list. So from 0, there are incident vertex is 2 and 1. So 2 and 1 is linked by linked list. Okay, so this is a linked list representation for G4 example. And that's all about how to represent graph using adjacent matrix and adjacent graph. Okay, so for the degree of a vertex in adjacency list means that number of nodes connected to this list. Okay, that's the degree of a vertex in undirected graph. And what is out degree of a vertex in directed? So interesting operation in linked list representation. Okay, so out degree of a vertex in digraph can be calculated using number of nodes in its adjacency list. Yes, it's the same as undirected graph. How about the in graph? In degree is not easy to calculate in linked list. So we must traverse the whole data structure, and then you can determine in degree of a vertex in digraph. Okay, so that's the difference. So out degree calculation is very easy, but in degree calculation is not easy. It's very difficult. So if you select linked list for graph, then you can see that in degree calculation is very, very difficult. But do you remember that it is very easy to calculate in degree if you are using adjacency matrix? Yes, in degree can be calculated using only column sum. Okay, so column sum is equals in degree of a digraph if you represent adjacency matrix. It was very easy for adjacency matrix, but for linked list in degree calculation is not easy. It's difficult. Okay, so you can decide which representation is better choice, better design, depending on the requirement of the algorithms. Okay, okay, let's go on. And third method is compact representations. Okay, compact representation is here. Okay, so this is example was a G4. So if we try to represent this graph in compact representation, compact means that we will store all data in a very small space, efficiently storing. Efficient representation is a compact representation. So this uses one-dimensional array. One-dimensional array. And this array, 0 will have okay, this index, this is the index of array. So index 0, 1, 2, 3, 4, 5, 6, 7. This 7 equals the number of vertex here. And this 0 will means number of vertex number 0. Okay, and 3 means the vertex 3. And the value of the array means that where the adjacent vertex will be stored. Okay, so this 9 means that this index 9. Okay, 9. Yes, so for vertex 0, we can see that we can see the adjacent vertex at index 9. So index 9 here. And 1 means that this one is incident vertex of vertex 0. Until where? We will see that next value of this array 1 at the index 1, the value is 11. So this means that 11, from 11, they will start to store for vertex 1. Okay, so this one is one set. And from 13, from 15, they will start to store adjacent vertex of vertex 2. Okay, this one until 15. 15 will store adjacent vertex of vertex 3. Okay, so this one until 17. And vertex 4 has only one adjacent vertex, 5. Okay, so at the 17 index, and the number is 5. And 18, number 5 has 2 adjacent vertex, 4 and 6. So it will be stored at index 18, this 18. So 2. And vertex number 6 will store adjacent vertex at index 20, 5 and 7. And vertex 7, last vertex, has only one adjacent vertex, 6. So at 22 index, we will store number 6. Okay, of course, the next index is 23. From this 23 index, it is available memory space. So the number index 8 will store where is free available memory space. It will start from 23. Okay, so it will store where the free available space. Okay, in this way, you can use one-dimensional array to represent graph. It is also very efficient representation method. But once you select this compact representation, the memory space can be saved very much, but it is not easy to calculate the every possible operation for graph. For example, can you calculate what is in degree or out degree in this representation method? In compared with the adjacency matrix, it was very easy to calculate the degree. But if you use compact representation, it is not easy to calculate the degree of each vertex. Okay, so this is a compact representation method. So can you understand that what is the most useful representation method? I think, of course, adjacency matrix is most common and the most useful. representation method for graph. Okay, and next was weighted edges. What was weighted edges? Weighted edges means that we have some values assigned weight for each edges. Okay, this weight represent some distance or cost from one vertex to another, and the graph with weight, the edge is called a network. Yes, this is a network. Network means it is a graph plus weight in each edges. That is network. Okay? Yes.